Well, greetings. Welcome back, Mr. Kolazar's class. We're going to start in today on video 3.3, and what we're going to be looking at is classifying matter. To begin with, what we're going to look at is classifying matter as a pure substance. Pure substances are matter with a uniform and unchanging composition. To begin with, uniform would mean same throughout. So an example would be salt. Sodium chloride is NaCl. If you had table salt, the first crystal of salt would be the same as the last crystal of salt. If we had pure water, it would all just be H2O, 2 hydrogens to 1 oxygen. As we're going, all of the water, same throughout from beginning to end. That would only be true for pure water. Most of the water, like tap water, has other things dissolved in it, so it wouldn't be a pure substance, it would be a mixture. Elements, on the other hand, is a pure substance that cannot be separated into similar substance by chemical or physical means. An element contains just one type of atom, so all the atoms in it are exactly the same. There are a total of 118 elements on the periodic table, of which 92 occur naturally. The other 26 are synthetic, meaning that they're man-made. So as we're going 92, technically 91, technetium is man-made, but we'll stick with just 92 are occurring naturally. Each element has its unique atomic number, which we'll talk about next chapter to be the number of protons, and composition, meaning each one is unique and has unique properties. As we're going to list out elements by their chemical symbol, which means that either the first or 2 or 3 letters will be given to an element. The first letter is always capitalized. The second or third letter is always lowercase. An example would be sodium is capital N with a lowercase a, making sure that we actually use a lowercase a, not a capital small a. We need to make sure that chlorine, capital C, lowercase l. It's important that we make sure that we have lowercase and capital letters in the correct placement when it comes to those symbols. Now our periodic table of the elements only includes elements, and it organizes them into periods and groups, which we'll focus on a little bit later on. Periods on the periodic table run from left to right, and our groups on the periodic table are columns running up and down. And so it's going to be a way that the table was organized by similar chemical and physical properties. Groups that are elements in the same group have similar chemical properties. So as we're going, anybody that's in this first group, or the second group, or third, fourth, all the way across to groups 17 and 18, have similar chemical properties as the arrangement of our periodic table. If the substance is listed on the PT, periodic table, then it is an element. Compounds now are pure substances made up of 2 or more elements that are chemically combined. Now, chemically combined means that we can only separate these elements by chemical changes. So chemically combined, when hydrogen and oxygen come together to form a new substance, H2O, they are chemically combined and can only be separated by chemical means like electricity. If we heat water up, it just turns into a gas, so it's still just water. So we can only by chemical means change those. Properties of the compounds are different than the elements that make them up. So that's the unusual part. Water, H2O, hydrogen, flammable gas, oxygen supports combustion, but when they come together to make water, both are gases. Water is a liquid, which actually helps put out fires, so much different there. A couple examples to continue this idea. 3.18 in the textbook talks about potassium, which is a metal that will explode in contact with air, and iodine, purple toxic gas, comes together to make potassium iodide, which is a salt that we sometimes consume in our diet. Explosive metal and a toxic gas. Similarly, if we wanted to check out one more example along these lines, sodium is a soft metal, explodes when it comes in contact with air. Chlorine was our first chemical warfare gas of World War I, noxious, toxic gas. When they chemically combine together, those two form sodium chloride or table salt, which we use on a regular basis. So much different than the two elements that came together to make them. Elements have different properties than the compounds that they're made from. So that's a key idea there. Now as we're going to look into when we put two or more of these pure substances together. Mixtures, when we combine two or more pure substances, as they're mixed, they retain their individual chemical properties. So anytime we mix two or more together, we get that. So an example would be salt and water. To make salt water, it still has the properties. You can taste the salt, and you still have the water's properties. They're just now mixed together. So as we're going mixtures, most things we see in everyday life are mixtures of different things. Our first type of mixture, to break it down, is going to be heterogeneous. Heterogeneous mixtures are different throughout, meaning the mixtures do not evenly blend. So it is not the same from top to bottom or left to right. Examples: Italian salad dressing, fresh squeezed orange juice, remember it would have to have pulp, granite, type of rock, salsa, a mixture of tomatoes, peppers, onions, always different no matter how it's made. All of the substances are distinct, meaning that as we're going, you could see or you could notice that the properties of one substance and the properties of another substance are both unique, or both the unique properties show up in that mixture. So heterogeneous mixtures, different throughout. Muddy water would be another example of different throughout. Homogeneous mixtures are mixtures that are the same throughout. So a mixture that has a uniform composition throughout, meaning that it's the same throughout. So individual substances are not distinct. You couldn't tell one part from another part. They'd all be very similar looking. More commonly, we're going to know them as solutions. So anytime you hear the word solutions, you can think of a homogeneous mixture. So are commonly called solutions. Example would be Kool-Aid. If it's made properly, Kool-Aid, the first glass of Kool-Aid would be the same as the last glass of Kool-Aid. The air we breathe in, fairly similar. Every breath we take is a fairly even mixture of gases. Dissolved gases in lakes, pretty much any clear water is going to be a solution with particles that are being dissolved inside of it evenly. Marshmallow, first bite of a marshmallow looks like the last bite of the marshmallow. Chemically, the mixture is the same throughout. Another example, vinegar. Vinegar is 95% water, 5% acetic acid. It's a clear solution, and in that clear solution, it's going to contain that exact ratio the entire time. Homogeneous mixtures, again, same throughout. An alloy is a special homogeneous mixture. Alloys are very useful in chemistry and in the science area for finding new and useful properties from both metals and non-metals when they're mixed together. An alloy, an example of one, brass and bronze we might have heard of, or even more important to us, steel. And both of these are in all three of those examples. Example here, we've got copper atoms and zinc atoms being alternated through. So as we're going, brass is when we actually have copper and zinc dissolved together in a solution, or not in a solution, but in a solid in this case. Or steel, a stronger version of iron. We have our iron atoms, but embedded in that iron atoms are some some carbon atoms. And that allows steel to be much stronger and more resilient and useful for many things. So manufacturers look at ways that we can maybe increase the durability or increase our strength to give us many unique properties that we hadn't seen or been able to use before. And so this is another example of a homogeneous mixture, same throughout. Next section we're going to look at is how we can separate those mixtures.